We're now finished discussing the chemistry of how monosaccharides are formed, that is, any single sugar. And our goal now is to start showing how we can put sugars together into larger structures. I want to start with the idea of a disaccharide, that is, taking two sugars and linking them together. And we're going to do that by forming a new linkage called a glycosidic bond. So this is in some ways parallel to what we've done in the past. We learned about single amino acids, and then we used peptide bonds to bring those two amino acids together and form a longer chain, a peptide or a protein. So a nice parallel there. Now before we get going, I'd like you to practice things a little bit. I'm going to start off by telling you that this is D-glucose on the right. I want to take these two sugars and put them together. And what I'd like you to do is pause the video for a moment and say, what are the differences between this sugar, D-glucose, and this one over here? There are two chemical changes, and let's start with that and see if we can identify what they are. Okay, I hope you can notice that the first difference is that the alcohol on carbon number 4 of D-glucose is changed in the left sugar. It's above. What that means is that this is an epimer. It's the C4 epimer. So you may or may not remember what that is, but I'll tell you. The C4 epimer is D-galactose. The second difference we have is that the anomeric alcohol on the D-glucose is down on the opposite side of the high-numbered exocyclic carbon. That makes it an alpha, whereas it's up and on the same side as that exocyclic flagpole carbon. That makes it a beta. So let's just make a side note of that. We'll say that this is a beta and that this is an alpha. Now, how do we do this? To bring these two together and form a bond, we're going to do much what we did before, and that is bring two functional groups together, two alcohols in this case, and we're going to remove an H, and an O. That is, we're going to remove the equivalent of a water. And we're going to then connect what is left over, and we end up with a glycosidic bond. Now, remember, this bond was above the ring. That's what made it beta. And that means the oxygen that is still part of that sugar is above the ring still. Now remember also that this alcohol was below the ring. That's what made it glucose instead of galactose. And it is still below the ring. It's just we've removed one of those oxygens and we are now sharing one oxygen between these two sugars. This is a glycosidic bond. Let's make a note of that. Glycosidic bond, two alcohols, remove a water, and you have what's essentially an ether bond, COC. So this sugar, by the way, is a very common disaccharide, and its name is lactose. Now, you don't need to know that and memorize the structure and memorize the name. I just mention it because it's found in milk, and it's going to be in your cereal or in human milk, and it's the sugars that provide energy from milk. Now, I do want you to know how to name these two sugars together as a disaccharide in a systematic way. And the way we do that is first name the two individual monosaccharides, D-gal and D-glic, and then we're going to do two additional things. Let's put a parentheses here, kind of a little bit more towards the glucose. And what we're going to do is put in the numbers of the two carbons that are connected. That is, we want to have this carbon's number and this carbon's number, and that's going to be 1 arrow 4. So make sure you go through those sugars and put out the numbers, label them on there, and we're going to connect those with an arrow and call it 1 arrow 4. That's easy enough. If you can number, we should be able to do that. Now here's the tricky part. The only piece that's missing for this name is the anomeric states. Now let's review that. we said that this oxygen, which is the anomeric alcohol now buried in a glycosidic linkage, that is above the ring on the same side, and that is going to be beta. And so what we do is we put a beta right there. The rule is that if you have an anomeric alcohol buried in a glycosidic linkage or participating in a glycosidic linkage, you must put the Greek letter for that. And the reason for that is because now this is no longer a free alcohol, and it cannot change from alpha to beta, or from beta to alpha, or to linear. It is now stuck. Remember, we said you can only linearize a cyclic sugar if the alcohol is free. Well, this anomeric alcohol is no longer free, and therefore the sugar on the left cannot mutarotate. It cannot linearize, and it's not able to do the tolerance test because it's stuck as a beta. This sugar over here still has a free anomeric. And what that means is this alcohol can mutarotate between alpha and beta. And this sugar over here can cyclize or uncyclize, and this portion is going to be able to do a tolerance test because it can uncyclize and become an aldehyde, can recyclize as the beta or recyclize as the alpha. So we have this funny mixture here. This is stuck as a cyclic, and we need to indicate that it's a beta. This is not stuck cyclic, and therefore we don't need to indicate that it's an alpha, because if you have this sugar in your milk, it's going to be mutarotating back and forth here. So the upshot is that lactose is D-galactose beta 1,4-D-glucose. Another way that's useful to think about this is that this linkage name, beta 1,4, corresponds just to the linkage. It's not trying to name the sugars. That's happening on the outer parts of the name here. The beta 1,4 simply refers to the beta of the one anomeric carbon of the left sugar connected to the fourth position of the right sugar. That's going to be a skill we practice. It's a tough one, but it's important for our biochemistry. Okay, I'd like to give you one that's a little harder. This is also a common sugar from your life. It's called sucrose. That's the kind of sugar you would put in your coffee or make pies out of or something like that. And let's go ahead and do what we did before. First, identify this sugar and this sugar. You should be able to find them somewhere else in your notes. Then name the linkage. So put it down here. We're going to have the sugar name on the left or top and the sugar name on the right. And then we'll have the connection in between. So let's go ahead and try that out, and we'll come back and tell you what the answer is. This one's a little tougher. Okay, definitely a good challenge here. The top sugar, not too bad. That's just D-glucose. The bottom is a 6-carbon keto sugar. That's D-fructose. Let's go ahead and do the numbering real quick. The glucose is 1, 2, 3, 4, 5, 6. Here's the tough part. Number 1 is way out there. Number 2 is right there. And then 3, 4, 5, 6. So what we have actually is a 1-2 linkage. That is the first carbon of glucose, the second carbon of fructose. And here's the even trickier part. The rule was we need to include a Greek letter for any time that we have an anomeric alcohol buried in a glycosidic linkage. Now the anomeric alcohol from glucose is off number 1. The anomeric from fructose is off number 2. What that means is we actually have both anomerics in sucrose involved in the linkage. And what that means is this is going to be called an alpha for the glucose side and a beta for the fructose side. So sucrose is glucose alpha beta 1,2 fructose. That's a tricky one. They won't get any harder than that. So let's stop our video here and move on.